Bismillahirrahmanirrahim. Dear students, we are starting today the second chapter of PRC2 course, which comes in the category of special topics, and the title of the chapter is Earthquake Design Basics for RCC Structures. So I'll be actually delivering you 3 lectures in this category, so that you may be able to understand the basic design parameters of RCC structures, keeping in view the seismic design. In today's lecture, the heading is Earthquake Design Philosophies, and this lecture is split into 2 parts. Initially, we will discuss the philosophy behind generation of earthquake force, and then later on we will be discussing the impact of this force into the RCC structures. Okay, earthquake occurrence, we are familiar with that earthquake basically occurs or results from the movement of the tectonic plates beneath the earth mantle. So far there have been 7 determined tectonic plates which create the earth crust mantle, and these tectonic plates, when slide in horizontal or vertical direction as can be seen in this figure, this movement of the tectonic plates towards each other or away from each other results in creating the fault line rupture. These are actually the fault lines. The joining lines of 2 tectonic plates are called natural fault lines below the earth, in the earth crust, and these fault lines rupture when there is slight movement between any 2 tectonic plates. Okay. Now what happens when there is movement in the tectonic plates? It is important to understand that the movement of the tectonic plates takes place below the earth mantle, as can be seen in this diagram, and this movement creates the rupturing of the fault line. For example, here the fault line has ruptured because of the movement of the tectonic plates. Now this point where the fault line has ruptured is called the focus point. This focus point then delivers the outcome of this rupturing at the mantle of the earth surface, at the mantle of the earth, and this point here is called epicenter. So we have got 2 points here, the focus point where there has been rupturing of the fault line, and we have got epicenter which represents the outcome of that rupturing. This thing is dependent on the vertical distance between the focus point and the epicenter, and this vertical distance is numerically called as focal depth. So it has been seen in the past that if the focal depth is of greater dimension, then the impact of this rupturing will be small at the epicenter. The rupturing results in creating mega acceleration, but the impact of that acceleration on the epicenter reduces if your focal depth is of greater distance. How much should be the focal depth, or how much distance is considered to be safe or less destructive? We'll discuss it in the later slides coming. Now another thing to note here is that this epicenter is the outcome of the rupturing of the fault line, and its impact on the structures depends on the distance of that structure from the epicenter. This distance is called horizontal distance or spacing, and it is numerically known as epicentral distance. So we have got 2 distances which are playing major role in putting the impact of the earthquake on a structure. Number 1, the focal depth. Number 2, the epicentral distance, normally called as ED. If your epicentral distance is more, then the impact of the earthquake will be huge at the epicenter, but the intensity will not be on the structure of that magnitude because it is far away from the epicenter. But if this structure or that city or that area lies close to the epicenter, then the ED reduces and vice versa, the impact increases. Now how that epicentral acceleration attempts or acts on a structure can be seen in this figure here, which is a 3D space model. You can see this is focus point and this is your epicenter. This epicenter has created waves on the mantle surface of the earth, the top surface of the earth, and these waves now are actually hitting the toe or the base of the structures which are present or which are coming in the way of these waves. Right, this is a structure, so this wave or these waves will hit that structure base, which will then transfer some force, some shear force to the top, up to the top of that structure. So this force is normally called as base shear, and the conversion of base shear at various heights of the structure are called story shears. So two types of shear forces are developed in every structure which lies in the way of the waves. One is called the base shear and the other are called the story shears. These two forces are also dependent again on these two things, the focal depth FD and the epicentral distance ED. Okay. In this slide we can see the various types of waves that can be generated due to a fault line rupture. When a fault rupturing occurs, then it results in creating four types of waves, which come under the heading of P waves, S waves, low waves or L waves, and we've got Rayleigh waves. So the geometry of these waves are different from each other, as can be seen in these figures. The P waves mostly travel in a straight node. There is no amplitude in these type of waves, whereas the S waves travel horizontally in a zigzag mode. Now this amplitude is not along the vertical direction, it is along the horizontal direction, like a snake movement. These two waves are called the body waves. Then these waves actually are further accompanied by the two other types of waves which are called as L waves, which creates an amplitudal presentation. You can see in these waves the behavior of the wave is not like a snake, it is like a snail. It is going up and down, and it is also covering the horizontal distance. And the waves, when L waves reached at the top surface of the earth, these are called as surface waves, which are of the same nature. They are having amplitude and they travel like a snail in the horizontal direction. These are the waves which mostly hit the structures which are present on the mantle of the earth. In the next slide, we are trying to understand the behavior of the wave impact on a structure. You can say this is a single story home or a room. You can see that, and this is showing the figure of the room or the house or the structure before the wave is hitting it. And you can see the wave is passing through the base, below the base. Once the wave passes through it and it comes right below the base, then it results in imparting some acceleration into the base of the structure, which then transfer it to the upper side or the superstructure, known as the story shear. So here we are having base shear, and here we will be having story shear. This story shear is resolved like this. If you remember the Newton's second law of motion, it is an inertia force. If there is an action, then there should be a reaction. So based on that Newton's second law of motion, if there is some impact on the base of the structure, it will result in drifting the structure at the on the upper side, known as superstructure, in the opposite direction. So the wave will be traveling in the forward direction, and the upper structure or the superstructure or the upper part of this structure will be traveling in the backward direction. And this is where the structures normally collapse or fail. The collapse or the failure of the structure normally takes place at the joints. This joint, this joint. This is called the straight column before the wave is hitting it, and this is the column of, this is the same column, but you can see after the wave has put an impact on that, then because of the inertia force, the column is showing the deflection or deformation along the central axis. So this joint might fail and this joint might also fail. Same is the case for this column. You can see here there is a drift and there is deflection. The lower part of the column is far away from the upper part of the column, which is going back. So there is some deformation along the axis of the column. So if the column is weaker in direction in the design or in cross section, it will fail somewhere here. But if the column is strong enough, but its connection with the slab and foundation is weak, then the column joints at the foundation and at the slab level will break. So in both cases there will be collapse of the structure. In the next slide, we are trying to understand the impact of the earthquake on the basis of ED, or the epicentral distance that I explained in the previous slides. You can see this is the yellow mark which represents the epicenter or the outcome of focus point, right? Now this epicenter has a magnitude, but its intensity reduces when the distance of the structure increases from the epicenter. The research shows us that the distance within the radius of 25 km from the epicenter is considered to be the most dangerous one, and this distance and the structures which lie on this diameter, where the radius of the epicenter distance is 25 km or smaller, then they will have maximum impact of the earthquake. We will be having the maximum impact of the earthquake on the structures which are lying in this zone of 25 km radius. We also call it as red zone, earthquake red zone. The second circle is representing the moderate period frequency of the earthquake, where the epicentral distance in terms of radius increases from 25 km and it can come up to, let's say, 50 km range. So the structures or the buildings or the cities which lie within epicentral distance of 50 km would be having also severe impact of earthquake, but it will be not as much as the structures or the cities which are lying very close to the epicenter or source of earthquake. So the numerical representation is 25 km and 50 km. Technically we call it as near field, which lies from 0 to 25 km, and intermediate fields which lie from 25 km to 50 km. Now those structures or cities which are after the length or the epicentral distance of 50 km, they are supposed to be comparatively safe than the structures or the cities or the areas which lie in these two ranges. Okay. Now as far as the building structures or infrastructures are concerned, then the risk of the failure of structures due to earthquake depends on the height of the structure as well. Now the theories and the research represent or concludes or suggests that those structures which are lying within the first area of field, this one here known as the near field area, they should have a story height of not more than 3 stories. It means the structures can be built on this line or in this area as well, but these structures should be low-rise structures, and the permissible number of stories that are recommendable are 1 story, 2 story, or at the maximum 3 story. As far as the moderate field of the earthquake intensity is concerned, which lies at a distance of, let's say, 50 km, then we can have structures up to 5 stories, but not more than that. However, those structures are areas which lie in the far field area, let's say 100 km, 200 km, 500 km, or more than that, then in that area we can go for high-rise structures having stories more than 5. It can be 10, it can be 15, it can be 20. So it is recommendable to construct low-rise structures in the near field and medium height structures in the moderate field and high-rise structures in the far field. The same will be presented in terms of seismic zones in the coming slides. In this slide, we can relate this seismic zone field, and we can convert this into various types of seismic zones. Now in this figure we can see the map of Pakistan, which has been converted into various seismic zones based on the geological studies and the data that is available to us. So on the right side you can see 5 boxes which have been colored with different which have been shown in different colors, starting from dark blue, light blue, green, orange and red. It means that in Pakistan, as far as the seismic design parameter is concerned, we can divide the whole country into 5 seismic zones. The zone 1 is represented by a dark blue line. It rarely exists in Pakistan because there are severe fault lines of huge I would say intensity as well in Pakistan. So actually Pakistan is lying on a tectonic plate which is considered to be very much frequent in movement. It is also known as Asian tectonic plate. So based on that, the non-seismic zone, zone 1 is also called as non-seismic zone. It is rarely existing in Pakistan, and you can see it's almost not more than 2 or 3% area in the whole country. However, the second seismic zone, which is known as moderate seismic zone, is called technically as seismic zone 2A, and this seismic zone is represented by light blue color or shade. You can see most of the area of the Punjab and Sindh province here lies in the seismic zone 2A, seismic zone 2A, whereas the seismic zone 2B is also called as moderate seismic zone. The moderate seismic zone has been further divided into 2 zones, the zone 2A and zone 2B. So 2B is also called moderate seismic zone, but in this case the seismic coefficient is a bit higher than the seismic coefficient for zone 2A. This green shade represents the most area of KPK province of our country, which lies in the seismic zone 2B. So it is also lying in the moderate seismic zone. Okay, and some area of the rural part of the province as well. Now the seismic zone 3, it is known as severe seismic zone, and in this seismic zone your central portion of the country is existing there, and also which includes some part of the Balochistan, I would say. So Balochistan, mostly parts are lying in the seismic zone 3 or the severe seismic zone, and some parts of the KPK province also are lying in the severe seismic zone. So this province in which we are which is our province, let me say, where we are sitting here presently, this province consists of the mixture of seismic zone 2A and seismic zone 2B. However, the upper part of Mansehra and Balakot are actually coming in the seismic zone 4, which is known as the red zone. So we are having a red zone part in this province as well, and some part of the Balochistan also comes in the category of red zone. This is also red zone. So we are having 2 red zones, or I would say 3 red zones in the country, which are numerically represented as the near field zones, where the fault line or the epicenter, possible epicenter, is at a distance of 20 to 25 kilometers. So these are the areas. Why we are studying these seismic zones? Because you cannot design the basic parameters of a structure for an earthquake if you don't understand the position of that structure, where the structure is lying, and you have to understand the possible seismic zone intensity. You have to take an intensity and convert this intensity into base shear, and then from that base shear we'll be calculating the story shear, something like this. So now you have clearly understood the Pakistan is having 5 seismic zones. The non-seismic zone are the minor seismic zone is rare. Mostly we are having the seismic zones of moderate intensity in Pakistan, represented by zone 2A and zone 2B. In this slide we are discussing some geometrical properties of structures on the basis of seismic designing. As far as seismic designing is concerned, first we will be discussing this figure. In this figure, 3 types of structures have been represented. This structure here is showing continuity along the x-axis and some continuity along the y-axis. Now this structure, you can see, is more in length along the x-axis than on the y-axis. So this structure can have a greater sway when there is an earthquake. To reduce that, we need to break it somewhere in the center. We have to introduce a structural joint here so that the intensity of earthquake along the base can be reduced. In this structure, you can see there has been extension of the structure both along the x-axis and y-axis. So this can be dangerous. We can have multiplication of seismic force along the story base, along the columns. We have to stop it. And it can be stopped by producing structural joint along the x-axis and along the y-axis. So we can convert this one structure into 4 blocks by introducing 2 structural joints. Then that structure will be more resistive, it will be more resistive against the earthquake intensity than this one here. In this figure you can see a tall building or a tall structure which is having very small catchment area. Now this is very dangerous because you are having a huge height, but the x and y direction is very small compared to this z direction. So you have to reduce the number of stories to balance that structure. Otherwise you can have failure of the structure when there is a transferring of wave at the bottom. In this figure we have been shown 4 or 5 types of structures based on the various geometrical figures. You can see this is called cylindrical structure. You can see it is elliptical in the surface area. So this is considered to be ideal as far as an earthquake is concerned or even a wind force is concerned. Cylindrical structure is most ideal. Same is a square structure of a small surface, of moderate surface area. You can see this is a structure which is very well proportioned along the x-axis, along the y-axis, and also along the z-axis. So this is suitable one. The third structure is of varying surface area. It is not square, it is not rectangular, but it is something which is balancing its surface area as far as the earthquake waves is concerned. So this is also ideal geometrical figure. And when you are having a curved structure, when a structure is designed along a curve, along a radius, then it can be designed like that. And this type of structure where you can have empty spaces in between the surface area, it is also recommendable, right? You can provide this type of structure as well. But this structure here, you can see it has been converted into 2 blocks. There is a square block and there is a linear block. Now this is not advisable because when there is movement of earthquake, then the drift of this block will be more than drift of this block, and there might be a collision here which can cause the failure of the columns or cracking in the columns, which almost it will result in the failure. So this is not the ideal condition. You can have a joint here as well to convert this block B again into 2 blocks. So that would be, I would say, a recommendable type of geometrical figure. Okay, in the next slide we are discussing the possible failure of structures when there is an earthquake. In the first figure again we are having 2 types of structures. One structure is having a height slightly smaller than the height of the adjacent structure. So when there is an earthquake, then the movement at the top of this structure will be different from the sway or movement of the high-rise structure which is adjacent to this one, which will result in a collision. This drift will cause the collision of the lower structure with the high rise structure, and this can cause the failure of the columns of the structure as well as the structure as well. So this is not the ideal case. When you are having two structures of various height being constructed at the same level, then you should have some distance between these two structures, and the distance is measured on the basis of the horizontal drift or movement. So let's say the horizontal drift of this structure is 5 feet at the time of earthquake, based on the basis of the earthquake zone, and the horizontal movement of this structure is, let's say, along at the top is 6 feet. This is called a drift. So we are having a 6 feet drift and we are having a 4 feet drift, something like this. So it is better to have a 7 feet distance between these two structures to make them safe at the time of earthquake. In this figure, a structure has been represented along the contour. You can see the structure is being elongated such that the lower part is not at the uniform bed. We are having foundations at various levels and they have been connected along the contour, and the structure has been raised upon. So there is a greater chance of the collapse of the structure because of the sliding factor. So it would be better that we should have converted this contour line into a horizontal ground by introducing a cut here and converting this structure into two parts, one like this and the other like this. So on the basis of that, these two foundations can be laid at one level, while these two foundations can be laid at the second level. So that would be more stable form as compared with this one. This is not the ideal case. It can cause a sliding with a slight magnitude of earthquake. In this structure we can see the movement of the structure at the free ends, which are actually the cantilever parts. So when you are having a structure and it is having cantilevers, these cantilevers can be critical at the time of earthquake, and you can have the failure right at these cantilever points. So they need to be either avoided or properly tackled. In this figure, what's happening is that we are having 1, 2, 3, 4 stories which are solid, but the bottom story is not solid. It is empty from the outer side. It is also called as soft story concept. So this story is critical now. This story can cause failure of the whole structure. It is represented in the next slide as well. You can see we are having a structure which is solid at the top floors, but at the first floor, which can be a ground floor, we are having a soft story, which means there have been openings introduced from all sides. This is a practical example. This is a residential flat or apartment building. You can see the flats being constructed at the upper floors, but at the lower floor we are having a parking facility, which can be called as we are having a parking floor. Now this parking floor needs to be properly tackled, otherwise it will act like a pendulum, because we are having a soft story at the bottom and hard stories at the top. When there is movement of the structure because of the earthquake, then the structure will be acting like a pendulum, which is weaker at the bottom and the weight is more at the top. It can cause the failure right at this point, or it can cause failure at the point of contact between the soft story column and the hard story columns. This can be the failure point. So these joints need to be properly designed, and these joints here need to be properly designed as well. Okay, so students, I think we have discussed the basics of seismic designing for RCC structures. In the next lecture, we will be discussing the codes of practice for seismic design of RCC structures in Pakistan. Till then, Allah Hafiz.